In this problem we have a circular horizontal pipe of internal diameter 150 millimeters. The pipe surface roughness is 0.06 millimeters and the pipe length is 150 meters. At this end of the pipe there is a pump which has an efficiency of 75%, and I've denoted the pump end as B and the other end as C. There is a fluid flowing through the pipe at a volumetric flow rate of 5 litres per second. The fluid properties are as follows. The density of the fluid given by the Greek letter rho is 850 kilograms per meter cubed, and the dynamic viscosity given by the Greek letter mu is 1.6 millinewton seconds per meter squared. The task is to calculate the actual pump power required to pump the fluid between points B and C to two significant figures. The solution is as follows. First of all, work out the cross-sectional area of the pipe, and I have denoted this by A. Since it is a circular pipe, the cross-sectional area will be a circle, and the area of a circle is given by pi times the diameter squared all over 4. Now 150 millimeters in meters is 0.15, which gives a cross-sectional area of the pipe as 0.0177 meters squared. The volumetric flow rate, rather than be in litres per second, needs to be in meters cubed per second. The volumetric flow rate is denoted by capital V with a dot above it, which means it is the rate of change of V volume with time. This conversion here will need to be used. 1 meter cubed is equivalent to 1000 litres, so to convert 5 litres per second into meters cubed per second, the 5 needs to be divided by this number here, 1000. So the volumetric flow rate is now 0.005 meters cubed per second. Since meters per second equals meters cubed per second all over meters squared, the velocity of the fluid flowing through the pipe, denoted by little v, can be worked out from this equation here. Since meters cubed per second is the volumetric flow rate, which we have just found, over meters squared, which is the cross-sectional area of the pipe, denoted by A. So substituting the two values in, the velocity of the fluid flowing through the pipe is 0.282 meters per second. The next step would be to find the Reynolds number. This is denoted by capital R E and is given by this equation here, where D is the diameter of the pipe, rho is the density of the fluid, V is the velocity of the fluid, and mu the dynamic viscosity of the fluid. Substituting our values in, but bearing in mind the dynamic viscosity is given as 1.6 millinewton seconds per meter squared. So this needs to be converted to, instead of millinewtons, to newtons. So a milli is a thousandths. So the actual value to substitute in would be 1.6 times 10 to the power of minus 3, giving an approximate value of the Reynolds number as 22,500. Now the frictional factor could be found using a chart, but this equation here is a good and accurate way to in fact find the frictional factor, denoted by letter F. Log here means log to base 10, so the friction factor will depend on the Reynolds number, RE, the surface roughness, E, as I've explained here, and D, the internal diameter of the pipe. Substituting in the appropriate values gives 1 over the square root of F equal to 6.229. So the square root of F equals 1 over 6.229. So to go from the square root of F to F, you need to square. So if the left hand side is squared, the right hand side needs to be squared, as here, to give a frictional factor of 0.026. Now the change in pressure from points B to C is denoted by this triangle here, and P is the pressure, and it's a drop because the pressure at C would be less than the pressure at B. Using this equation here, the pressure drop along the pipe is given by this equation. So substituting our value of the friction factor as 0.026. Now L over D can either be in meters or millimeters, but they must be in the same units. So I have substituted the length of the pipe as being 150 meters, and the diameter hence must be in meters also. So 150 millimeters is 0.15 meters. The density of the fluid is 850 kilograms per meter cubed, and the velocity, which was worked out here, needs to be squared, giving an overall pressure drop along the pipe of 7,030 pascals. Now power equals work done per second, and work done is force times distance. So power is actually force times distance per second, and distance per second, or distance over time, is in fact velocity. So power can be written as force times velocity. Also, P, pressure, is force over area. Rearranging to make force the subject gives force equals pressure times area. So now we have power equals force, which is pressure times area, times velocity, which is little v, and as we found up here, the velocity of the fluid is in fact the volumetric flow rate divided by the cross-sectional area of the pipe. So substituting the velocity as volumetric flow rate over cross-sectional area, you can notice here that this A cancels with this A, so the power of the pump is given by the pressure times the volumetric flow rate. So the actual pump power required will be pressure, in this case the drop in pressure, delta P drop, times the volumetric flow rate divided by the efficiency eta. So substituting our pressure drop as 7,030 pascals, our volumetric flow rate as 0.005 meters cubed per second, the efficiency 75%, which as a decimal is 0.75, gives an overall actual power of the pump required as 47 watts.